Hey everyone, welcome to this video. And we are going to run this encoder only transformer bert.ipynb file. In case you're wondering why, remember that an encoder only transformer we will use later is bert. So that's what this file is all about. So download this file from the course directory, upload it, change your runtime type to a GPU so that our code does not run very slow and runs fast. Then go to this link here, create an account, download the data, and upload a spam.csv file. So yes, once you have a GPU being used and the data uploaded, go to runtime and press run all, which I've already done. And let's explain what the code does. First off, we import Torch, tell the code to use a GPU so that it runs faster. And let's check out what our spam.csv file looks like. You get a bunch of columns and rows. The last three columns are NAN, so it doesn't look like there's any useful data here. You get some messages and a ham or spam classification, where the ham classification means not spam, so it could be things like, hey, I'm joking around, or let's hang out. Whereas a spam classification does look somewhat obvious, right? Like, hey, you won a free car, or you won a free microwave or something. Anyways, I will get rid of these three columns here, and I will rename the V1 and V2 column with my code in this cell. And so now we have message and is spam of ham or spam. But let's change the values for is spam to, if it is spam, give it a value of 1. Otherwise, 0. So cool. This message that is, oh, you won something for free, is spam of 1. And so now our data looks good to go. But there's an issue where if we do .value counts, is spam 0 has a count of almost 5,000, and is spam of 1 has a count of about 1,000. So our data is imbalanced. So a question you might have is, why is imbalanced data an issue? Imagine you have 100 animal images, 95 dog images, and 5 cat images, and we want to create a model that accurately determines dog images versus cat images. You could create a model that always guesses dog images, which would give you a misleading or inaccurate 95% accuracy on those 100 animal images, when the reality is your model has a 0% accuracy for cat images. So I'd run some code here, and I essentially just trim our data and force the count to be equal. So we're forced to shrink our data to make it more balanced. And then we can do a sanity check that it is balanced. So if we look at like 10 random things, we have about 5 zeros and 5 ones, which is pretty cool. So our data does look balanced now. And as we learned in the course, we're going to have training data, validation data, and test data. But because our data has shrunken in size so much to force it to be balanced, let's skip the validation set so that we can use as much data as possible for training. And say we'll have a training set and a test set now, with the test size being about 20%. When working with text data, let's use a tokenizer, which I will import here. And now let's see the tokenizer in action. For Kevin is great ! We get input IDs back and a attention mask back. So we'll create train tokenized data and test tokenized data from the tokenizer. I'll create a class called custom dataset. Now the code here could be a little bit complex, but just focus on this last part. We return the input IDs and the attention mask. No surprises there because that's what the tokenizer returns. And then we return is spam, which will be, well, 0 or 1. We create a train data set and a test data set from the train tokenized data and the test tokenized data. As we learned in the course, we will use mini-batch stochastic gradient descent with batch size of 64. And then, yeah, an encoder-only transformer we will use later, BERT. We will not create our model from scratch. So model equals distilbert for sequence classification dot from pre-trained, distilbert base uncased, blah, blah, blah. For our optimizer, we will use Atom. And during training, we will have 5 epochs. And nothing here should be new to you. There's a forward pass where we get outputs from the model, get the loss, do back propagation, where we compute the gradients, update weights, and during training, we will calculate the batch loss and the batch accuracy so we can see how well our model is doing during training, and we'll do a bunch of printing. And the results during training are pretty promising. Our train loss goes from 0.58 and decreases to 0.04. More intuitively, the train accuracy goes from 87% to 99%. But as we learned, again, earlier on in the course, just because your model does really well during training does not necessarily mean it will do well on new data. The analogy being, if our model was like a college student doing well during training is like saying a college student does really well while studying. But just because that college student does well while studying doesn't mean they'll do well on a practice test or the final test. So let's see how well our student does on the final exam or the final test. Pretty good actually, 98.44%. So this model / student analogy I've made, the student does better during training, but not by much. So final test accuracy, 98.44%. And then let's try out our model on like our own data. I've created a helper function called predict message where, what do you know, we use the model. And then I've created some of my own custom messages where the first two will hopefully not be classified as spam, right? The first message is essentially, hey, let's hang out. The second message is, when will you arrive here? The last two messages, hopefully, are more likely to be classified as spam, right? Like, you are approved for a credit card, or congratulations, you just want a free card or a free microwave, etc. And here's a for loop. And what do you know? The first two messages, they have a 98% and then a 97.52%, right? And then once you get down to the last two messages, those probabilities are reversed. So yeah, it looks like our model does a pretty fantastic job at differentiating between spam and not spam. And even though this code wasn't too crazy complex, it was relatively simple. The one thing I want you to remember from this video is this. It's that when order matters in our data, such as translation or a message to someone, right? We can use RNNs, which use hidden state or memory, or we can use transformers, which uses attention. And in this video, we showed through our model and code that attention works. It gave us 98.44% final test accuracy. So attention works, attention is real, and attention is a viable alternative for working with order in data compared to, well, hidden state and memory. All right, that's it for this video. Thanks for watching.